Okay, I'll give you an idea on how to get going on this homework example, and then I'll give the answer. Find the electric field at point P near a half circle of charge with uniform linear charge density lambda. So we've got a rod and we've built it into half a circle. First thing you do is identify a little bit of charge dq. You draw the electric field created by that little bit of charge dq, that's dE. Show the components dEx and dEy. Think about the symmetry. See that EY is the integral of DEY equals 0. Your EX is going to be the integral of DEX. And DEX you got to find with your trig. So it's going to be DE. I'll call this angle theta, which makes this angle theta, DE times sine theta. Okay, DE equals K, times DQ over R squared. DQ is equal to lambda times a length element. The length of our little bit of charge is a little bit along a circle, which is ds. ds is arc length. You might remember from high school that arc length is equal to radius times angle. So it's equal to r times d theta. Okay, you've got to put this in for your dq, this in for your dE, and do your integrals over the limits of theta. Your theta goes from one end of the rod, that's when theta equals 0, to the other end of the rod, that's where theta equals pi. And when you do all that work, what you should get for your final answer is that the electric field vector is equal to 2 times k times lambda divided by r in the plus x direction. This one's a bit trickier, so I'll try and give you a little bit of extra guidance. For this one, we have our line of charge, but it has a variable charge density. It depends on where you are along the rod. We still start by picking dq. We still draw dE. And we still draw dEx and dEy. Let's write down our dE first. dE equals k times dq over r squared. R is the distance from the charge to the point. It's the radius of the circle. dq is lambda times the length element. The length of our little bit of charge is a little bit of the arc, ds. This time, what we have to fill in for lambda is a times s times ds divided by r squared, and we're still going to use that s equals r times theta. So we get k times a times r times theta times r times d theta. S is r times theta, ds is r times d theta divided by r squared. What we see here is that we've got two r's on top, cancels with the r squared on bottom. So it gives us dE has a magnitude of k times a times theta times d theta. So then next, to find our EX, it's going to be the integral of dEx, which is going to be the integral of dE. I'm going to pick this one for my theta, which makes this one theta. So it's dE times sine theta. Fill in for my dE. I get integral of k times a times theta times sine theta times d theta. I'm evaluating over the limits of theta, and theta is going to go from 0 to pi. Okay, and then this matches what we expect about our charge density, that the density is 0 up here and it's big down here. So it all lines up here. We haven't made any mistakes. Take our constants out front. We've got k times a outside of the integral from 0 to pi, theta, sine theta, d theta. This integral right here, you can do an integration by parts, or you can look this up online. The integral of theta sine theta d theta is equal to sine theta minus theta times cosine theta. Okay, so that should be far enough for the x component. We'll also walk through the y component. Our y component now is adjacent to our angle, so EY is the integral of DEY, which is the integral of DE times cosine theta, which is the integral of K times A times theta times cos theta d theta. Okay, so we've got to do our integral from 0 to pi. Take our constants out front, that's K and A, integral from 0 to pi of theta cos theta d theta. You can look this up if you wish. The result for this integral of theta cos theta d theta is theta times sine theta plus cos theta. Okay, so that's how you evaluate those components. Your final answer should give you that your y component is minus 2 times k times a. That's your y component. And your x component is plus pi times k times a, and that's in the x direction. So there's the net electric field due to that ring. Let's have a look at this problem now. It's a fair bit of kinematics, but there's also some electric fields and forces involved here. We have a small object with mass m and charge q, and it's got an initial speed of 5,000 meters per second. It's projected into a uniform electric field, so right off the bat we know there's going to be a force, between two parallel metal plates with length 26 centimeters. There's an electric field between the plates that points down with magnitude of 800 newtons per coulomb. The object passes on through without hitting the lower plate. After it passes through, then it gets deflected further downward, so it ends up 1.25 centimeters underneath its original path. We're told to ignore gravity and air resistance, and we want to find the charge to mass ratio. What is Q over M? So why don't we have a look at the path here? What happens to this charged particle as it moves? And then we'll think about how we're going to analyze it. I'm going to draw out the path on a copied image of this picture on the next slide. Here's our zoomed in image. Let's see if we can think about that path now. While the charged particle is between the plates of the capacitor, it's going to feel an electric force because F equals Q times E. If there's a force, then there's an acceleration, so it's going to deflect downwards. There'll be a curved path somewhat down. When it leaves the area of the capacitor, there's no more force because we're told to ignore gravity. That means it carries on in a straight line with the same velocity. Okay, I've exaggerated the motion a little bit compared to the previous slide just to make it a little easier to see. So if we think about what happens inside the plates, it deflects down by a distance equals y1. If we think about what happens outside the plates, it deflects down by a distance y2. And then all together, those distances add together to give a distance of d, which we're told is 1.25 centimeters down. So we know how far down it deflects. We know it's comprised of two vertical distances, y1 and y2. And we know that together, y1 plus y2 equals d. We can write down something for y1 and write down something for y2. Then we can put those together and we should be able to find our charge to mass ratio. Let's get started on y1 first. Let's write down a kinematics equation to see if we can find y1. We know that y is equal to, or y1 I suppose we'll say, is equal to v0 y1, so the y component of the initial velocity times time t1, the amount of time it spends in the first region, plus 1/2 times a1, the acceleration in the first region, times t1 squared. Okay, right off the bat, v initial y1 equals 0 because it comes in horizontally. So our first term is gone. Don't have to worry about that guy. Next, A1 is the acceleration in region 1, the 26 centimeter long capacitor. We know that acceleration is force over mass because F equals ma. And we know that force is charge times electric field. The force points down because the electric field points down. So minus QE over m. Our electric field E is 800 newtons per coulomb. To keep things simple, I'm going to drop my units here. If you prefer to keep them in, you certainly may. What is our time t1? Well, let's think about the horizontal motion. We know that the distance it travels x1, 26 centimeters, is the x component of velocity, v initial x for the first region, times t1. So our t1 then is going to be x1 over vox1, 26 centimeters, put that in meters, divided by the velocity, which is 5,000 meters per second. And we get t1 is equal to 5.2 times 10 to the minus 5 seconds. Okay, let's put this together for our y1. We've got 1/2 times minus q over m times 800 times 5.2 times 10 to the minus 5 squared. Run all that through the calculator and what we get is minus 1.0816 times 10 to the minus 6 times q over m. Q over m is the charge to mass ratio. That's what we're trying to find. Okay, we've got our y1. Next we'll get our y2, and then we'll put them together to find our q over m. Let's use a similar strategy now to find our y2. y2 equals v0 y2, so our initial component of y velocity when it's in the second region, times t2 plus 1/2 times a2 times t2 squared. Right off the bat, a2 is equal to 0. We're told there's no field outside the capacitor, and we're also told to ignore gravity. That makes this entire term 0. Okay, what next? What is our v0 to y? v0 to y is the y component of velocity when the charge leaves the area of the electric field. So voy2 is equal to voy1 when it starts in the electric field plus the acceleration times time. The acceleration when it's in the field times the time it spends in the field. We're trying to find a final velocity, the velocity when it leaves the capacitor. voy1, that's 0. a1, we found that on the previous slide, that's minus q over m times 800. t1 we also found on the previous slide, 5.2 times 10 to the minus 5 seconds. That gives us a voy2 of minus 0.0416 times q over m. Okay, the other thing we have to sort out, what is our t2? How long does it take to travel the 56 centimeters? We know that x2 is vox, the x component of velocity, in the second region, times t2. The x component of velocity never ever changes because there's no horizontal acceleration. So we'll solve for our t2. It's x2 over vox2, 56 centimeters, which we put in meters, divided by the velocity in the x direction, 5,000 meters per second. That never changed at all. Gives us 1.12 times 10 to the minus 4 seconds. Okay, let's put these two guys together. y2 is equal to minus 0.0416 times q over m times t2, which is 1.12 times 10 to the minus 4 seconds. Multiply those guys to get minus 4.6592 times 10 to the minus 6 q over m. Okay, we've got our y1, we've got our y2, we know our d. Let's find our q over m. Let's fill in our values now. y1 is minus 1.0816 times 10 to the minus 6 q over m. y2 is 4.6592 times 10 to the minus 6 q over m. D is 1.25 centimeters. It points down, so it's negative, and then we'll convert to meters. So we can solve for q over m then, and we get 2,177. Charge over mass means our units are coulombs over kilograms. This question has two very large horizontal sheets, a little distance apart, and equal and opposite charge. This is a capacitor. So we have two sheets with equal and opposite charge. We don't know which is negative and which is positive. You want to use these sheets to hold stationary in the region between them. So somewhere in here, a little oil droplet that has a mass of 462 micrograms. So here's our charged oil droplet in here. Mass is 462 micrograms. That's 10 to the minus 6 grams. Remember, a gram is 1,000th of a kilogram. So the mass is 462 times 10 to the minus 9 kilograms. It says that our oil droplet has an excess of 5 electrons. That's telling us that the charge of the oil droplet is equal to minus 5 times the fundamental charge, E, 1.6 times 10 to the minus 19. Assume that the drop is in a vacuum. So which way should the electric field point if this little droplet is going to stay still? So if we think about why it stays still, we know that there is a downward force on it. That's the force due to gravity. That's equal to its weight. In order for it to stay still, there must be an upward force. And that's the electric force. So since Fg is down, Fe is up. We remember that electric force Fe is equal to the charge times the electric field, and that charge is negative. So the electric field would be the electric force divided by a negative number. All that to say that the electric field has to point down. So when the charge is negative, we know that the force and field are in opposite directions. We can draw that on our picture if we wish. If the electric field points down, it means our upper plate is positive and our lower plate is negative. To figure out sigma, let's think about doing Newton's second law here. So the sum of the forces equal, if you hear that crashing, my dog is investigating some boxes. The net force is the mass times the acceleration. The net force is the electric force up, subtract the weight down. That has to equal 0 because it's stationary. The electric force is the magnitude of charge times the magnitude of the field, subtract mg, equals 0. The magnitude of the charge is 5 times the fundamental charge. Our electric field between the plates of a capacitor is sigma over epsilon naught, minus mg equals 0. That leads us to solving to find that our charge density is m times g times epsilon naught divided by 5 times e, or 50.1 coulombs per meter squared. Pretty big charge density. This question feels a bit Jedi, so maybe I'll walk you through this one a bit. We have a thin disk with a circular hole at the center. This is called an annulus. So we had a solid disk, but we drilled out a bit from the center. Or maybe it looks like a flat donut. It has an inner radius of R1 and an outer radius of R2. The disk has a uniform positive surface charge density sigma on its surface. First thing we want to do is find the total electric charge on our object. So what we'll remember here for part A is that total charge equals density times area. That little bit is easy enough to understand. It's the area part that might be a bit tougher. So area means the area of the annulus. I might call that A. For the area of the annulus, so that's sigma times A, what we have is our big disk. If it were completely solid, it would have an area of pi times its radius squared. But it's not completely solid. We've drilled out a circle in the center, so we have to subtract this amount of area because we took that out. Okay, so then this gives us our expression for our charge. Q is equal to sigma times pi times R2 squared minus R1 squared. In this part of the question now, we're trying to find the electric field around our annulus. Let's build on the idea that we used when we found the net charge. And that's the idea that our annulus, this solid disk with a little hole cut out of the center, consists of a big solid disk of radius R2, subtract a little disk with radius R1. Okay, so that means that the electric field of our annulus would be the electric field of this big solid disk. I'll call that E2 because it had radius R2. Take away the electric field of this little disk. Okay, hopefully that idea makes sense. This object is just this one with this thing cut out of the center of it. Make sure we know what our coordinate system is. We're taking our x-axis going straight up through the center, concentric with all of them. Now, the good news is we already know the electric field of a disk. We can write down the expression of these two, then we subtract them to get our total electric field. So our electric field then is the electric field of the bigger disk, which is sigma over 2 epsilon naught times 1 minus x over square root of x squared plus r2 squared. Then we're subtracting the electric field of the little disk, sigma over 2 epsilon naught, 1 minus x over square root of x squared plus r1 squared. It is a vector, it's all in the x direction, so that's the I direction. So there's our answer. We can neaten that up a little bit. We can take our sigma over 2 epsilon naught outside of everything. We get 1 minus x over square root of x squared plus r2 squared. Subtract 1 plus x over square root of x2 squared plus r1 squared. That's all in the I direction. We've got plus 1 minus 1, so they go away. And then we're left with our electric field. We can take our x outside or leave it in. I think I'll take it outside. Sigma times x over 2 epsilon naught times 1 over the square root of x squared plus r1 squared. Subtract 1 over the square root of x squared plus r2 squared. And the direction of that electric field, I'm going to say, is away from the annulus. It's a positive charge, so the electric field points away. On top it points up, below it points down, so we'll just call it away. In part C here, we're asked to find that to show that at points on the x-axis that are sufficiently close to the origin, so somewhere about here and somewhere about here, the magnitude of the electric field is about proportional to the distance between the center of the annulus and the point. So we're asked to show that the electric field is about proportional to x, and to say what values of x is that true for. So when I look at my expression I found in part B, I saw that the electric field was sigma over 2 epsilon naught times x, so there's a proportionality, but I have all this stuff in here. What I'd like to do is think about for what conditions would all of this stuff become about constant. So I'm going to think if my x1, or if my x is a lot smaller than my r1. Okay, so that's one condition that just pops to mind because I see this right here. If x is a lot smaller than r1, then what that means is that x squared plus r1 squared is about equal to r1 squared because my x is a lot smaller than my r1. Okay, so x is so tiny compared to r1 that when we add it on, it doesn't really do anything. The implication of that is that 1 over the square root of x squared plus r1 squared is about equal to 1 over the square root of r1 squared, which is equal to 1 over r1. Likewise, if x is a lot smaller than r1, r1 is already smaller than r2, so x is also a lot smaller than r2. So if x is smaller than r1, it's also smaller than r2. So then we can also have 1 over the square root of x squared plus r2 squared is about equal to, that x becomes even more negligible, the square root of r2 squared, which is 1 over r2. Then for our electric field is approximately equal to sigma over 2 epsilon naught times x outside of 1 over r1 subtract 1 over r2, which is equal to sigma over 2 epsilon naught times 1 over r1 subtract 1 over r2 times x. All of this stuff in front of the x is constant. That means that E is proportional to x. And this expression that we just found right here is only true if x is much smaller than r1. So there's part C done. This last question is pretty neat. It says a point particle with mass m and negative charge q is allowed to move along the x-axis, but it can't move off the x-axis, so it's constrained to stay along here. The particle is originally placed at rest at x equals 0.01 times r1. So this is telling us at a position where x is a lot smaller than r1. So it's placed right about here somewhere and released. Now the question is a bit loaded. Find the frequency of oscillation of the particle. So first of all, frequency of oscillation. Why does this oscillate? Does that make sense? So let's think about what's going on here. The electric force on the particle is equal to the charge of the particle minus Q times the electric field. So the force on the particle is minus Q times sigma over 2 epsilon naught times 1 over R1 subtract 1 over R2 times X. If we look at this, we see that all this stuff right here is constant. Our force has a negative sign in front of the equation, and it has a dependence on x. Hopefully this is a little bit reminiscent of Hooke's law that said a spring force was minus k times x. Let's just take a moment to remember what that means. In Hooke's law, we saw that any force, when we discussed this sort of thing with simple harmonic motion, any force that's opposite the displacement, in other words, a restoring force or a force that pushes towards equilibrium. So any force that's opposite in direction to the displacement and proportional to the displacement results in simple harmonic motion. That's what we have here. A force is in opposite direction to the displacement and it's proportional to the displacement. So this force is a restoring force, which results in simple harmonic motion or simple harmonic oscillation. The constant of proportionality, what we would call K, is equal to minus Q times sigma over 2 epsilon naught times 1 over R1 minus 1 over R2. And we can get our frequency from this value of K. Oops, sorry, I said that K had the negative sign in it. K does not have the negative sign in it. K is this bit right here, the constant of proportionality. To get our frequency of oscillation, we remember that our angular frequency would be the square root of that constant divided by the mass, and that's equal to 2 times pi times f. So our frequency of oscillation is 1 over 2 pi times the square root of our constant of proportionality divided by the mass, or 1 over 2 pi times the square root of Q times sigma over 2 epsilon naught m 1 over R1 minus 1 over R2. So if we place that little particle at this point on the axis and let it go, it would bounce back and forth between those 2 points with this frequency.